Let's talk about the heating blanket. You guys ever use one or have one at home? Heating blanket. Yeah? Plug it in, right? Put it on. Very nice. I'm just going to call it a heater. Okay? Here's a heater. Let's talk about a heater. A heater obviously is just something that warms up, right? When your grandmother has arthritis, right? Her hands really hurt. She likes to bake cookies, but it's hard for her to bake cookies because her hand hurts. So you buy her, right? Because you're a smart biomedical engineer. You buy her a little heating blanket and you say, grandma, right? Whatever you call her, right? Grandma, almost no one's grandma. Everyone's a something, right? Put your hands in this for a little bit. It'll feel nice and warm. And then afterwards, take them out and your hands will feel better. She does it and lo and behold, she feels better, right? Maybe not, but she might. Your uncle has back pain. You say, oh, I got it. Look, put it on your back for a little while and it'll cure it, right? Now, there's something very remarkable happening here. Heat cures arthritis. If you learn about arthritis, you'll learn it's very, very complicated. There's all these molecular changes, whatever it is, ligaments, bones, all that. Heat, back pain, the nervous system, the brain, and you put a little heating blanket on it, right? So this is an example where the heater is being used as a treatment, right? And this arrow here is not at all obvious, right? What else could you use a heater for, right? Are there other things you could apply heat to the body to in order to address those issues? Stiffness, swelling, I don't know, all kinds of stuff, right? This arrow here, right, is a very interesting arrow. And if you think about this arrow, so I like to get a little philosophical, okay? And you're trapped. You have to listen to anything I say, So it's interesting, right, with being a teacher. After you're done, I say hi to you in the hallway. You don't have to say hi back, right? But now you have to listen to me. So here we go. I think it's really useful to not just do circuits. I think it's very useful for you to take a bigger picture view, to understand conceptually why we're doing what we're doing. Because I think ultimately when you do become the head of R&D at Medtronic, that's the kind of knowledge that you're really going to is going to set you apart from the other people. This arrow here, all right, is the key. Curing arthritis with a glove that you put on and applies heat in a certain way, right? Beautiful. And now arthritis is gone. What an amazing invention, right? Now, I would say that if you wanted to make a little heater, right, I think you could go to an electrical engineer, right? I think they could do it. They would understand, right, batteries and other stuff. You will too in about 10 minutes, but they could do it, right? Maybe a mechanical engineer, the heaters come with like a little blanket. Maybe the one you used had a blanket or something. I'm sure a mechanical engineer might help you pick the right kind of cloth to make sure it's nice and comfortable. That's great, right? But how hot should it get? I mean, the body, let's say the body's 37, right? Should it be 37? Should it be 40? 50? Where should they put it? On the hand? On both sides of the hand? How long should they put it on for? Right? Grandma wants to know. Should it be there for 10 minutes once a day? 1 hour? And then never again? So, electrical engineer doesn't know. Because I could do whatever you want. You want it to go to 50 degrees? I'll make it go to 50 degrees. The mechanical engineer says you want it in the shape of a glove? It's in the shape of a glove. but what? Now, on the treatment side, right, certainly the people we go to first are the doctors, right? So there may be a doctor that your grandma sees who specializes in arthritis. He knows all about arthritis. He went to medical school. He knows about biology. He knows about everything else, right? But the doctor doesn't know about heating blankets, does he? Right? He wouldn't know how to make one, right? Let's say he really doesn't even know what temperature is. I don't know. That's a bit of an extreme thing, right? But maybe he doesn't understand the principles of how a heating blanket might work, right? So he's also a bit unsure how to design it, right? So to go from here to here, you sort of need someone who understands both sides of the equation. You need to have someone who understands things like how a heating blanket would work, right? The kind of power source you might need and so on, right? But you also need to understand maybe a little bit about the source of arthritis, but also ultimately this key question of, how long should grandma wear it? And what should the temperature be of it? And that is biomedical engineering. Right? That's biomedical engineering. Biomedical engineering is both literally and conceptually at the interface between the devices and the body. And it is the hardest part of the problem. Yes?
Would icy hot be considered like that?
Right, but that's a mechanical thing, right? It's not a device, isn't it? Oh no, they make a device also? It's gel. So in this class, we're going to be focusing more on instruments, but it's the same sort of idea, right? Where it's a gel, it's a packet, you do something. That is correct. That's a biomedical engineering problem where, first of all, you have to have someone who understands that there are materials that if you snap them or combine them, go through some sort of exothermic reaction. And someone would also understand how to control that reaction in order to produce a certain temperature rise. I think that's a great space for a chemical engineer. Nonetheless, they need to know, what's the target temperature? Is it for back pain? And so on, right? And so this is exactly where we live as biomedical engineers. We will learn, we can learn about this, we can learn about this, and I'm also going to tell you that this is where the breakthroughs come in. This is where the breakthroughs come in treatment, all right? The reason we don't have a device that can, I don't know, cure cancer isn't because we don't have a fast enough processor. It isn't because we don't have a hard disk large enough to store a lot of information. It's a biomedical engineering problem, all right? As were the development of COVID tests, as were the development of glucose meters. At the heart of it was always a biomedical engineer, and we will see that. Now, sorry, here's on the, this is talking about on the treatment side, okay? Now, I'm not going to redraw it, but this is going the opposite way, all right? You have a device, right? Set your time. This should go on for 3 minutes, right? We have a circuit, and then we have something that touches grandma, all right? And when it goes this way, we can call it a transducer, all right? But all sensors are transducers. Not all transducers are sensors. So if you go this way, I can say sensor, and I can say transducer. But if we're going the other way, like in the case of ultrasound, we're going to say transducer. We're not going to say sensor because it's going the other way. All right. How would you make a heating blanket, right? You have to start from zero, right? You have to make a heating blanket. So this is how you'd make it. I brought one. All right. We have a 9-volt battery. You've seen this before, right? Okay. And you guys know what this is? It's a resistor. All right. What I'm going to do is I'm going to take my 9-volt battery and I'm going to take these little pins of the resistor and I'm going to hold it like that. So just like this, okay? So now I've done something, I've built something, okay? All right. All right. I want you to do it. And I want you to tell, and I want you to, then after you do it, I want you to tell me if you feel something. You can't hurt yourself with this. So go ahead and make the connection, and then you can count, as long as the connection is there, count to, I don't know, 10 seconds.
I feel heat.
Feels heat. Okay. So all of you can repeat this experiment, right? The heat was specifically, by the way, here. The transducer. Oh, but you said it was a resistor, Professor, correct? Okay? But right, but something was happening here, and this is it. What did we just make? What's that? We made a circuit. Now, to draw out what I just did, I took a battery, 9 volts. I took this thing. If you look closely, it doesn't have to be curved, right? This object, right? It was a resistor. Talk about what that is, but it's, and right, I did that. No problem. You all saw it happen, right? Now, we're going to represent this, right? This is a circuit, but when we draw out circuits, we don't use this kind of notation, we use a different notation, right? This is going to be represented as a voltage source. And here I'm using the word voltage, so we'll talk about what that means. And we will use this symbol to indicate the resistor. A voltage source, we could think of it as like an ideal battery. And just like a battery has a voltage, right? A voltage source will also, let's say that this is a 9-volt voltage source. Now, I am well aware that all of you have had at least a full semester of circuits, right? And so some of the things I'm going to be saying are a bit repetitive. Nonetheless, I'm going to be saying things a bit differently than the way you've seen. Now, when you took circuits, and so now you see all of a sudden we're in the world of circuits, right? Circuits, right? That's why it's the circuits. Now, when you're taking a circuits class and you had to do a problem, right? It was sort of like circuits for the sake of circuits, right? Find all the currents in this. But in this class, it's different. In this class, it's circuits for the purpose of making something useful. So it's going to be a little bit different. Nonetheless, we're going to cover, so we use notation that looks like this, but obviously there is no voltage source that is a little two-dimensional sphere. So in reality, we go here. And so in this class, right, you're going to get very comfortable because we have a lab-based component, right, of going from these kind of images to these kind of images, right? And so this is our symbol for a voltage source, as you know, and this is a symbol for a resistor, right? Now, what is a resistor? Anything is a resistor. This is a resistor. It's a resistor. This is a resistor, though I mean there's some stuff in here. And even this is a resistor. It's all resistors, right? There's nothing special about a resistor. It's just a piece of something, a piece of material, all right? Now, when we use resistors to build stuff, we put these little connectors on them, right? Because that helps us build stuff out of them, right? So that's why they have these little tails on them, right? And you'll notice that every resistor has 2 ends, like a lot of circuit components have 2 ends. And there's different types of resistors, right? There are resistors which, we describe resistors, right, in terms of their resistance, and the units of that are in ohms. And so, for example, a resistor might have a value of, let's make it simple, 1 ohm. Now, different resistors, I know I'm telling you stuff you already know, right? I know this is very basic, but we're going to build it up, right? Because I also want to demystify what this thing is. This thing has a certain resistance. Now, it turns out this has a rather high resistance because of what it's made out of, because it's made out of cardboard, all right? Let's ignore what's attached. This, pretty sure, has a very low resistance, right? Because what it's made out of metal, right? Now, even if this was a lot bigger than this, I would still say this has less resistance. So the resistance of something is very much dependent on what it's made out of, right? And so this thing was made at the resistor factory, and the materials that were used to make out of it were very carefully selected, right, in order to give it a 1 ohm resistor, a 1 ohm resistance. Whereas the same factory made other resistors and they had a 2 ohm resistance, and they're not going to be twice as big, right? They're just going to be made out of a different material. All right, so yes.
Earlier you had mentioned that in the case with the battery and the resistor was a transducer. So would it be fair to say that a transducer is not based on a component, but also
Yeah, that's one way. Yeah, you could say that. Yeah, exactly. Yeah, one person's resistor is another person's transducer. Sure, I like that. Okay. And so now we have gone from a physical reality, right, to a circuit diagram, right? And it's a very simple circuit where we have a voltage source connected to a resistor, but something happened, right? Obviously, the resistor heated up. And the question is, why did it heat up? How much did it heat up? And so on. All right. When a voltage source is connected to a resistor, right, something happens where current flows through the resistor. And you've seen this concept before, right? Current is the flow of charge, the flow of electrons. You can use all kinds of analogies for this. Maybe you like to think of a pressure difference and then a pipe, and the pipe could be very narrow or very big, and now you have flow, right? Now how much flow you get will depend on both the pressure and the size of the pipe. And the same thing happens here. How much current you get, right? How much flow of charge starts to happen here will depend on both these parameters. Okay. Ohm's law. States that if you have a resistor, R, and there's a voltage across that resistance, the current that flows through will be given by I, right? And we get this relationship. Am I writing big enough? V equals I R. This is in units of volts. This is in units of amps or amperes, and this is in resistant units of ohms. So for example, if I have a situation where I have 1 amp flowing through a 2 ohm resistor, I know that the voltage has to be 2 volts. If I knew the voltage was 2 volts, right, so this was sort of my unknown here. Here's my unknown here. If I know that I have 10 volts and there's a 2 ohm resistor, then I know that the resulting current, right, must be 5 amps. Now that's Ohm's law. And it is the single most important equation in this course. This equation will get you through a third of the course. And it's not that bad of an equation, and I know that you've applied it right in the circuits class, right? So that will be it for the review of Ohm's law, all right? Now, we go to this situation here, where I put these two things together, right? And then after putting them together, I realize that this is the appropriate circuit drawing of it. And once I've done that, I understand that actually, right, there is an application of Ohm's law here that will tell me how much current is flowing through, right? And so we can see that the current is going to be equal to, in this case, and let me use the exact values that we have here, right, is going to equal to 9 volts divided by 1 ohm. And so the current here is going to be 9 amps. Now these, I should say right now, are not exactly realistic values. Okay, we're not going to get that much current out of it. But now we know that there's some current flowing through here. Great. Why does it heat up? All right, why is it heating up? So now we need to introduce another, we don't know, there's nothing here about heating up, right? Did that come up in circus class, right? The professors say, and now the heat, no, where's the heat, right? Turns out that as current drives through a resistor, right, it will heat up that resistor. And that is a principle called Joule heat. Right? Here we credit someone named Ohms. Here, right, we credit someone named Joule, right? Or at least the units come from Joule heat, right? And Joule heat says that if you have a resistor and there's current flowing through it, I, and that resistor is R, right? The amount of heat, the amount of Joule heat that you're going to generate is going to be related to I squared R. All right, meaning the more I you have, the more heat you're going to generate. The more R you have, the more heat you're going to generate. Right? And this doesn't exactly tell us, okay, is it going to be, I want to know if it's going to be 35 degrees, is it going to be 40 degrees? That's going to be a little bit more complicated, right? That's going to depend on things like time and other things as well. But the combination of Ohm's law and Joule heat creates a heating blanket. And so we can see here, right, that if you were to plug in these values, we would say, well, for our specific case, right, the Joule heat is going to be proportional to 9 amps squared times 1 ohm. If we had no current, right, we would have less going on. Okay, very interesting. Now, you may say, I'm really happy about this. Heating Blanket Incorporated is, we're ready to launch, right, our product. But I couldn't help but notice that, where is it? You know, that the company that makes these resistors, as I already mentioned, they don't just make a 1 ohm, they make a 2 ohm, right? Meaning, I could put the 2 ohm on it, I could put the 1 ohm on it, right? Now, what do you do? Well, one option you would say is, who cares? Put 1 ohm on some, put some ohm on 2, grandma will be just fine, right? Maybe say, I don't think so, right? Maybe say, I don't think so. I think it really matters. And so now you're trying to figure out, well, how does it matter, right? How does it matter? Well, we have equations here. So, I mean, there's one way to do things. One is you take the resistor and you put the 1 ohm, and then you take the 2 ohm, right? And sure, you could measure that empirically. You could ask ChatGPT, right? But you do have these equations here, right, that might tell you what's going on, right? So you might go here, and you might say, oh, I see what's going on here. The more resistance I have, right, if resistance goes up, all things being equal, right, big asterisk on that, if resistance goes up, will I get more heat or less heat? More. So you would say that if I put a 2 ohm resistor instead of a 1 ohm resistor, I'm going to get the extra heat version. So now I have, you know, heater and heater deluxe, right? And the heater deluxe, the only difference is that I've put a 2 ohm resistor here, right? And as a result of that, right, I get more heat. But then you make them and you realize that the exact opposite happens. You make them and you realize that in fact, when you went from 1 ohm to 2 ohm, you got less heat. So not so deluxe, right? And the reason is, we have 2 things that matter here, right? We have the resistance, but we also have the current. Now I said if all things being equal, if this term is fixed, obviously increasing the resistance will increase heat. But we know that the current will change. How will the current change? What's that?
It goes
it goes to, right, so you're saying that if this is, let's call this scenario 1, scenario A. Now in scenario B, we will write I equals 9 volts over 2 ohms equals 4.5 amps. You just applied Ohm's law, right? You just used it. And you can see that by going to 2 ohms, we lost half the current. Oh. Well, this one became twice as big. This one became twice as small, but all things are not equal, right? Because we have the square. So now we see that we got less, right? Now, I want to put a little, take a step back here. Are you ever going to work at Heating Blanket Incorporated? The chances of that are extremely small. Please email me in 10 years. When we go through examples in this class, it's not because we care about the specific examples. It's because they are teaching us something that is universal. And what you're learning here is we're using circuits to figure out what resistor we should use. And another name for that is design. You need to design a heating blanket, right? And you need to pick between the 1 ohm and the 2 ohm. And this is a great way to help you try to figure out which one you should use because we're using this theory, okay? Now, it turns out we can actually rewrite this because we have an equation for I. So in fact, Ohm's law also says that I is equal to voltage over resistance, right? That's equivalent, right? And so what I can do here is I can replace this I, right, equivalently. This is going to be an equal with a V over R, right? And the V will be squared. And actually, we're going to end up with, I'm just going to jump to the end, V squared over R. This and this are the same because of Ohm's law, right?
I have a question. How does joule heat relate to like Fahrenheit? Like, is there a calculation?
So now things like the size of the resistor will matter, and the temperature of the room will matter. So there are some additional calculations there, right? You've taken classes where you've talked about things called heat capacity, right? In some other class. So there's other things that will start to matter, all right? Or if there's an insulation around here, things like thermal conductivity, right? So so it's a great question because it shows you how when you're making medical instruments, it's not one domain. It's not just electrical engineering. It's not just mechanical engineering or heat transfer, right? And it's not just materials, like making the blanket. It's all of them, which is why biomedical engineers have to be adept at all those domains because that's how instruments are made. You don't have to, I suppose, right? You can work just on one piece of it, but someone needs to understand that. Doesn't someone at the company need to understand how all those pieces come together? Someone does, right? So once again, we see how it's a biomedical type of problem, right? That's the approach we take here. So we have this equation, and this maybe is a little bit easier because now we see very directly. Now the voltage here is set, right? The voltage here is 9 volts. Getting a little messy here, right? We're going to square it. And now we have just the R, right? And that's why I put this squiggly line here. It's how that gets translated to temperature is a little bit more complicated, but certainly this is what's going to be pushing the system. And so now we see that if we increase the resistance, right, we're going to produce less heat. And so what you're seeing here is an example of how we went from a physical object to a drawing, and how that drawing then helped us do something. Now you can say, I don't like it. I'm just going to get the 2 resistors and I'm just going to put them together. And that's it, right? I don't like math. All right, but you know, they don't just make a 1 ohm and the 2 ohm. They make a 2.5 ohm. And they also make a 3 kilo ohm, 3,000 ohm. Which one? oh, I'm going to measure them all. You could. It's going to take more and more time, right? And there's also the other issue we talked about how that the joule heat translates to temperature and so on. I'm not saying at some point you don't need to build it and measure it in this class, in the labs. At some point, right, you're going to have to just build it and see if it works or not. But to sit there and randomly insert components, hoping that it'll work just right, will not lead to success. You must have some theory that you are using. Even if you ask me, how does this relate to temperature? Even if the theory is not complete, even if there's something you don't know, you can still use the pieces that you have. And so what I'm trying to show you here is, again, we don't care about heating blankets. I'm trying to show you here how basic circuit theory will be used in biomedical instrumentation. And it's not a particularly high level, Ohm's law.